Me a few seconds and there we go. Okay, so the plan for today is to just finish this kind of general thoughts part of the discussion from day one. So in day one, we just kind of introduced one another, and then we talked about some of the administrative details, some of the material that's in Blackboard and so on. Again, if you haven't done that already, go through Blackboard, read through all those materials carefully. It has all of the course policies and so on listed in the syllabus and all of that. Even take notes in the front of your notebook so that you can refer back to some important points later on. And then make sure that you're logged on to WebAssign. So again, you can use the 2-week free trial on that if you're still working out financial aid or any of that kind of stuff. So you can get in, today, right after class, get started on that homework. There is one section of homework due this coming Sunday, and then this morning I'll have the chapter 2 homework posted and available with some tentative due dates. So chapter 2 won't be due this Sunday. It'll be due, it's the Sunday that's a little over a week from now. So that is our plan for today. Finish the discussion from day 1 and then start in the chapter 2. So before we get started, are there any questions on anything from last time? Any questions on the administrative side of things, on WebAssign? Anybody have a question on any of that? Okay. Of course, you can always email me or WebAssign message me. A couple folks have WebAssign messaged me already. So you can always reach me outside of class that way. And as I mentioned last time, I'll have my office hours posted probably tomorrow afternoon after kind of everything settles down with my schedule and I'm pretty sure everything's going to land. Then I'll set my office hours and post them. That will also be available via Zoom. All right, one of the other things that I do is each day I have a quote of the day. So whatever kind of strikes me for that day or whatever, I think goes well with what we're doing in class or something like that. So the quote of the day today is from P.T. Barnum, the famous circus entrepreneur. And it's a bit of a long quote, but the crux of it is true economy consists in always making the income exceed the outgo. We want there to be a margin in favor of the income. And of course, he's in this example speaking financially, and as students, that's usually not going to be the case for you. But I think these ideas about margin in favor of the income do apply much more broadly in life. So something that I personally see is, when I'm driving around, I tend to get frustrated at other drivers. I think that's a pretty common, human trait these days. But I realized that my chance of getting frustrated and the amount of frustrated I get is much higher if I'm, say, running late or if I'm just on time and I need to make that light to stay on time. If the person in front of me, stops at a yellow or something, I'm much more frustrated than if I maybe left myself a little bit of margin, maybe left 5 minutes early. If I'm running a little bit early and I hit an extra red light, no big deal. And I find this applies to a lot of things in my life, that I'm happier, less stressed, less annoyed, less annoying to be around when I build margin into my life. A more maybe concise way of saying this: when you have margin, catastrophes often become inconveniences, and when you have no margin, inconveniences often become catastrophes. Where does that apply to a student's life? Well, probably in lots of situations, but one very practical example is, when you're looking at doing your homework and you say, okay, the homework is due Sunday night, 11:59 p.m. Well, if you say, okay, I think this homework is going to take me 2 to 3 hours to complete, and I'm going to plan to start it at 8 p.m., 9 p.m. on Sunday, you've left yourself no margin, right? And then if anything goes wrong, if you're not feeling well that day, the power goes out, there's a technical issue that takes a little while to get sorted out, well, then you missed the deadline for the homework. Right, that minor inconvenience turns into a much more annoying inconvenience, I suppose. Maybe missing a homework is not a catastrophe in life, but certainly would rather not miss a homework. On the other hand, if you say, okay, I'm going to plan out my work so that I say work on my homework a half an hour every day for each day, Monday through Sunday, and then maybe if I finish early, I have Saturday and Sunday off. if you plan it out that way, and then, Tuesday there's a tech glitch during the time that you plan to work on your homework, not a big deal. You can kick Tuesday's 30 minutes to Wednesday, do an hour on Wednesday, when that technical glitch gets sorted out, or, if you're not feeling so great on Tuesday, sleep in a little bit, and then on Wednesday, come back and hit the homework hard, right? You have a lot of margin. There's a lot of buffer there. There's a lot of wiggle room for other options. Uh, Maybe not such a big deal on homeworks, but definitely a big deal on exams. Remember, there are no exam due date extensions. Since the exams are open for a week each, that should be more than enough time to work around any issues that may come up. But again, if the exam is due Sunday night and you wait until Sunday afternoon or night, some people, I can see the times that people start on my end, and some people wait until Sunday at 10 p.m. or something to start their exam. And if you do that and anything goes wrong, you have no margin. Sunday night, there are going to be no options. There's no libraries open, no coffee shops open to go to take that exam. So I think, um, probably the number one thing you can do to set yourself up for success in college is trying to build margin into your studies. And it's also, probably the one of the harder things to do, because it's just so tempting to just procrastinate, push it off a little bit. Some people work well under pressure, but that's usually not a great way to learn. So, and don't get me wrong, I mess this up all the time. Your faculty members mess this up all the time. We all, everybody is human. Nobody's perfect, but getting a little bit better at it has really good benefits. Okay, so that's the quote of the day today. That's one of, I think, the main thoughts for the course as well. And you'll hear me, harp about that each time an exam comes up. I'll say many times, do not wait until the last minute. Plan, take it well in advance, all of that. Okay, so this is just wrapping up our kind of intro discussion from day one. Some general thoughts about college education. And this is something a little new that I'm doing this semester, just to try to give students a little bit of the perspective of what your faculty kind of look at when we think of college education, and to try to communicate. There's a lot of questions these days about, is college education worth it at all? Or if it is worth it, in some sense, why do I need to take all of these extra courses? I'm going to try to answer that question, and I think um, maybe a convincing way, but at least in a way that gives you a uh, a view into our perspective, into the perspective of, I think, most faculty. So the first thing I'd like to address is the different types of college courses. Um, so, going throughout your college career, you're probably going to take courses in 3 different areas. And I kind of, roughly divide these last 2 areas into 2. Some people have them kind of as just a single area. But, let's say that you're interested in nursing, right? You're going to have your program-specific coursework. These are going to be your nursing classes where you're actually learning about, how to treat patients or how to care for patients, or, learning the things that you're going to do day to day. You say, what I'm doing in this class looks pretty much exactly like some aspect of my job that I'm going to be doing every day. Or if you're in business management, these are going to be like your management courses. They're saying you should manage people this way, you should not manage people that way. And you say, okay, I can take that one-to-one right over to my career where I'm managing people and say, okay, I should do this, not do this when I'm doing my job. There are also program-related courses. So these would be kind of the ancillary things. If you're in business, well, if you're a manager, you're not an accountant, but you need to know a little bit about accounting. So you can develop budgets, so you can put together financial statements that look reasonable, so you can read other people's financial statements. You need to know a little bit about the language of business, and that's accounting. So if you're in business management, your accounting course might be a program related thing. You say, okay, I'm not going to be an accountant, but I see that this is clearly something that I really need to know to function in this field. Or if you're a nurse, you need to know a little bit about, math to be able to do dosage calculations, or maybe you need to know some statistics to be able to evaluate some of the research, right? This research paper comes out, might affect the standard of care for your patients. Is it a good piece of research? Is it, kind of a questionable piece of research? And then there's general education. So these are sometimes called core curriculum or, gen ed courses, something like that. And I think these are the ones that people that, the most kind of ask about. So the business major says, well, why do I have to take an art class? The nursing major says, why do I have to take a philosophy or humanities class? Right? The graphic design major says, why do I have to take a math class? And the answer is, well, that's the general education core. And what's the purpose of a general education core? People say, well, you know, why are you making me take classes that don't appear to directly apply to my field, to my career? And I think there are several answers people try to give to this. And so basically, when somebody says, "Why do I need to know this?" is that's implicitly what they're asking. Why do I need to take this course? Why is this general education, this core curriculum, part of the required coursework? Um, I think there are several answers that, have some merit, but I think really miss the mark. And they're unfortunately the most common answers that math instructors give. One of them is, oh, it's like doing mental push-ups. You're training yourself to think logically. I think that's not a great argument for why you should take math because there are lots of things that you can do to train yourself to think logically. You could take a course in how to play Settlers of Catan really well. I mean, that's going to train you to think logically and strategically, possibly even to a higher level than a math course, or take a course in how to play chess very well. I mean, if you want to see logical and strategic thinking. uh, if people say it's like mental push-ups, it's like, well, okay, everything that you do in college is like mental push-ups, right? You're making yourself better at learning things and so on. Um, one of the answers, which I think is a valid statement, but it doesn't really get to the heart of the answer. One of the answers is, well, you're going to need math, even if you don't use it in your career, like if you go to take out a car loan or a home loan, or, if you're teaching your kids or you want to help your kids with homework or any of that, these very practical answers. I think they're good answers and they might be compelling to some people, but I think most people say, well, if I want to take out a home loan and I need to understand the math, if I find it valuable, then I can find a resource myself and learn it then. So what's the purpose of learning in college? There are a couple other ones that off the top of my head I can't remember, and of course my little notes are in the other room, but I think uh, I think those are the two most common ones. Oh, and there's a third one. Well, if you're planning to go into this field and you decide, a year or two into your studies that you want to pivot into a different field, having a math background or having a broad general education background gives you a lot more options. Again, I think that's a very true statement. It's a very valuable statement. Um, but then people will say, well, why isn't that my choice? If I want to limit my own options, why isn't that my choice to do so? I think um, the most accurate answer to the question, why do I need to take general education, um, comes out of this quote that I like from The Truman Show. The Truman Show was a movie with Jim Carrey. He mostly did, funny, crazy, off the wall movies, but this Truman Show was a little more of a serious movie, and it's a little bit old now, but the story of the show is that Truman, the main character, Jim Carrey's character, is the subject of a reality show. So there's all these cameras, all these actors that are interacting with him as he's going about life. But the thing is, he doesn't realize he's on the show. He was, from the day he was born, he was part of this community that was all constructed around him artificially to be part of this reality show that's broadcast all over the world. It's in this huge dome. They built this huge city just for him. And you know, he's never left the city. He thinks that he's living real life, and it's really just all a show. And at some point, strange things happen every once in a while, glitches happen, and you think like, how does he not realize that he's in the show? And one of the characters asks Christoph, the kind of the mastermind, the producer of the show, um, you know, how has he gotten to whatever 30 years old or something and not realized that he's living on a TV set? Like these strange things happen and they always kind of find a way to justify it to him or tell the actors what to say to kind of cover it up. And Christoph says, we accept the reality of the world with which we're presented. It's as simple as that. And I think this quote is really um, the main argument for having a general education curriculum, a core curriculum, um, sometimes just called a humanities curriculum, although these days we tend to use that word a little more narrowly. Right? Each one of us has grown up in a certain household in a certain area. We have certain family members. We have a certain worldview, certain experiences that we're exposed to. And there are a lot of other people who've had very different experiences to you. That could be on the other side of the world. That could be, a few miles down the road. And I think through the general education core, it gives us some perspective on, the merits of the different ways of thinking, the idea that the understanding that different ways of thinking exist, that there are different modes of thought. You could think very logically, like in a math course, or you could think more abstractly, like in an art course. Um, and just exposing you to those different life experiences of tons of different people, and those maybe having a chance to see the value of those different modes of thought. I think that's really the idea behind the Gen Ed core. And I would add to that a second thought that if you think historically, maybe say more than 100 years ago, almost everybody, with the exception of aristocrats and super rich people, the only things that they really had the time or energy or ability to learn were things directly related to their job. If somebody was a farmer, they had to learn farming. If somebody was, a tanner, they had to learn, leather work. Well, in the last maybe 100 years or so, ballpark, this idea of, the ability to study philosophy, the ability to study mathematics, the ability to study subjects that don't directly relate to your field, has become available to essentially everybody, right? I mean, everybody who goes through K to 12 education gets schooling in all of these areas: how to read, how to write, uh, how to compose an argument. And I really see it as unfortunate that we're almost backsliding, right? We're almost saying, uh, for as much as we appreciate equality and equity and all of that these days, we're almost saying, well, let's take all of those general education courses, the things that don't relate directly to my job, and kick them to the side. And then it's going to be back to the elite in some sense, that are going to be the only ones who study those, and they're going to be the ones directing society, right? Having a general education core allows you to really understand at a deeper level your place in society and in the world, and to direct your society in the way that you want it to go, and not really just be kind of buffeted around by the folks who have studied, political philosophy and all of these things. So I think that's at least from my point of view, the most compelling argument for the existence of a gen ed core. Again, the other statements are true. It's, mental exercise and helps you think logically, and helps you, help your kids with homework. And, you can save a bunch of money when you realize that, well, this mortgage is a better option than that mortgage from a different bank. Those are all true statements, and those are all good. But I think that's really the crux of the argument for the existence of a gen ed curriculum. And really, kind of overall, the goal of college is to create lifelong learners, especially these days in this world. um, Fields change so quickly that you have to continually be learning, and understanding how you learn and learning how to learn independently is a large part of college, right? You're going to have to keep learning in order to just keep up with your field, to say nothing of the fact that maybe you get 10 years into your field and get burnt out, don't want to do that job anymore, maybe pick up an injury and you can't do that job anymore, and you want to pivot to a different job. that's going to be a lot of learning. That's going to be a lot of taking an initiative and so on to make that pivot mid-career. A couple pieces of advice about college in general is the first thing that I didn't appreciate as a student, and took me even a little while to appreciate as a faculty member, is that success in college is as much about mastery of time management and expectations as it is about mastery of the coursework, right? So time management, I mean, I've already touched on this a little bit with the discussion of margin. And again, I'm not saying this from a place of superiority. I'm not saying that I'm the best at time management or, I goof up on this often and all of your faculty members do as well. And all of you will as well. Everybody, goofs up on it, but getting better at this over time is the goal. So time management, just how do you allocate your time between, between work, between school, between personal and family responsibilities, between friendships and, sleep and, kind of just keeping your mental health in check, just having some rest and relaxation. How do you allocate your time between all of those things? And doing so in a very mindful way, right? Facebook can easily go, or maybe it's TikTok these days, or maybe it's not TikTok these days. I don't know with getting rid of it, but it can easily go from, all right, I'm going to chill for 30 minutes to, 3 hours later, you look up and wait, what happened there? So being very deliberate about time management is especially important in remote and online courses. For whatever reason, it's much easier to kind of procrastinate and let time slip by in remote or online courses than it is in in-person courses, even though even in in-person college courses, most of the work is still done outside of class. But for some reason, it's just that like physical touching base a couple of times a week. Maybe it feels a little more accountable or something. I'm not sure what it is, but it seems to be a little harder in remote and harder still in fully online. Also, things like expectations, things like professionalism, right? When you write an email to a faculty member, it should be, somewhat formal and professional. And when I write you emails, it will be also formal and professional. That doesn't mean you can't be nice and polite, it doesn't have to be cold, um, but certainly shouldn't contain curse words and things like that, right? Things like being in class on time, uh, having a screen name that's appropriate, just things like that. So the expectations of the course, and of course, just adhering to the course policies. The syllabus outlines the policies. Those policies will be pretty rigidly adhered to, and that's out of fairness to everybody in the class. If I start changing the policies for each person, then nobody really knows what the policies are. Nobody's really taking the same course, and nobody's grade at the end of the course really means the same thing as anybody else's grade. So just things like, again, taking the initiative, being proactive, doing things like setting aside 30 minutes a day every day to study rather than 3 or 6 hours, all in one big chunk. It's really hard to learn material that way. You might make it through the homework. If you do that, you might be able to chug through the homework in one big chunk, but how much you're going to retain from that for the exam is going to be pretty limited, at least for most people. And really, something that I've come to appreciate more and more, the more things, the more different fields I've tried to study, is there really is no substitute to time spent with the material, right? I mean, you just have to sit down and do it. There's not a hack, there's not a cheat code, there's not a way to say, okay, well, if only I have the right the right book or the right study materials or find the right YouTube lectures, then I'll be able to do 1 hour work per week instead of 6 and get an A in the course. There really is no substitute to time spent with the material, whatever you're studying, whether it's math or your art class or your nursing class or your business class, whatever it may be. You really just have to put in the time with the material. And in college, that's, that time expectation is pretty substantial. Things like setting intermediate deadlines are super helpful. So if you have, a homework that's due on Sunday and there's, I don't know, let's say 40 questions on that homework, maybe it's, they're shorter questions. So more questions, or maybe it's a couple sections that are due, and in total it's 40 questions. Well, if your goal is be done by Sunday, that's kind of a hard goal to keep track of on Monday, Tuesday, Wednesday, right? Am I making good enough progress, or am I going to get to Sunday morning and realize, oh, I have like most of the homework still to do, even though I have been working whatever time per day I had allotted. Well, set intermediate deadlines, right? By on Thursday morning, I'm going to check in and I'm going to make sure that I have about half of my questions completed. If I have less than that, then maybe I need to allocate a little extra time, Thursday, Friday, Saturday, to get caught up. Maybe that was a more challenging section than I'd initially realized, or vice versa, right? Maybe I'm way ahead of the game and I can say, okay, I can either repurpose some of that time toward other classes. I think I'm going to be done, with my homework on Thursday or Friday, or maybe I can just, give that time back to myself as just leisure time, just whatever you like to do. Um, so setting intermediate deadlines, where are you going to check in to see what your progress looks like? And courses that have, projects or term papers is even more important, right? Maybe you set a deadline of, okay, I have a paper due in 8 weeks. Well, 2 weeks from now, I want to have read at least, two of the three pieces of source material that are going to go into this. And 2 weeks after that, I want to have a fully fleshed out outline for the paper. And 2 weeks after that, I want to have a rough draft where all of the ideas are on paper, but it's maybe not super clean, and then that week, I want to meet with my professor in office hours to kind of look over the rough draft, see what they think about it. And then a week after that, I'll have the polished version completed and turned in, right? Something like that is a much better strategy than just saying, okay, 8 weeks from now, I need to have a paper, polished, completed, and turned in. So setting intermediate deadlines like that for yourself can help a lot. And also these days, just eliminating distractions, whether that's turning your phone off or physically putting your phone in another room. Sometimes I have to do that if I'm having a day where I'm especially tempted to look at my phone, every other minute. Put your phone in another room and, go in a different room and do your studying or your homework or whatever. Having the TV on in the background seems like something you can multitask. It's like, oh, I can put on a kind of a brain break type show in the background and do my homework, but that really distracts you more than you might realize. At least it does for me. And I think it does for most people. And even people, people are great, family is great, but like sometimes, if you're trying to like, watch a kid and talk to a spouse and do homework all at the same time, it's just a little too much. Can you find a time or a location where you can kind of be by yourself and, folks can be in the other room doing something and you can be doing your homework. So, um, yeah, I think I discussed this a little bit already. And then I think the last thing, just really quickly to touch on here, is that in each course, and again, this goes for math courses, but I think for basically every college course, there are kind of two things that are addressed. And the balance of, what percentage is what can differ depending on the level of the course or the field. But there's two ideas of kind of the body of knowledge versus the way of thinking, or the material of the field versus the method of the field. So in math, things like, knowing what all the symbols mean and knowing what all the rules are for how you proceed with a calculation versus the method versus just the kind of underlying philosophy of the field, right? In math, your arguments are going to have to be very rigid and logical. In something like philosophy, there might be a little less rigidity expected. In something like art, much less rigidity, right? So what is going to be a kind of a persuasive argument or statement or product in a given field is going to depend a little bit on what that field is, right? The method is a little different. The method of approach for that field is going to be a little different than another. And we'll just wrap up with a question. And I think this is a good question to take maybe 10, 15 minutes, just think about and maybe write down one paragraph for each of these two sub questions in a notebook. This isn't something for a grade. That's not something I want you to turn into me or anything like that. But you're in college to learn things and to end up knowing things. And I think it's good for you to just ask yourself, give a little bit of thought to, from your perspective, what does it mean to know something? Right? I mean, we use this word very flippantly, this word know. In other languages, there are actually, multiple words for know. But things like, I know what my name is, that's kind of a different kind of know than when I say I know that 3 + 5 is 8. That's a kind of different type of knowledge. Or if I say that I know that if I, hold something above the ground and let go of it, it falls down until it hits the ground. I know that to be true, but I know that on a different basis than how I know my name or how I know 3 + 5 is 8. So what does it mean to you to know something, right? And this isn't a question with an answer, right? I mean, in math, one of the nice things about teaching math is that our questions always have very clear answers. This is a question of philosophy. It doesn't have a clear answer as far as I can tell. There's a whole field of philosophy, a subfield, epistemology that is devoted to essentially what does it mean to know something? And it's not a clear answer, but at least give a little bit of thought to it. I think it's worth it. And clearly directly related to that, what does it mean to learn? Right. This might help just philosophically guide your path as a student. What do you want your experience to look like in college? Right. Um, okay, so those are some thoughts in general about college education. Um, Probably not as smooth as some of my other intro material, because like I said, this is kind of my first semester doing this, so I'm fleshing it out as I go along. Um, but I think that these are some things that I didn't appreciate as a student and really even as a faculty member until the last couple of years. And I think this is important for us to relay to students, to give you a little bit of insight into what the perspective of some of your faculty is and, kind of educators in general, what our perspective is, and hopefully give some amount of an answer to why do I have to learn this and what can I do to be successful in college. So hopefully this gives you some valuable information. All right, any questions on anything up to this point? Anything from day one? Anything from the administrative side of things? Okay, let me get my windows moved around here a little bit. Oh, just changing my setup around. This is one of the downsides of remote is that I, have one view that I'm showing you guys and a different view on my end, and it's not as easy as just shuffling a paper for my notes or whatever. So like an in-class class, but okay, there we go. All right, so moving into the course material properly now. Our goal today is to just quickly kind of recall some topics that you've likely seen a couple of times before in your academic career. If you took Math 80 with us, this would be either built into Math 80 or maybe globbed onto the end of Math 80, depending on how your instructor decided to cover it. Or if you've, had some algebra in the past, have done any review, anything like that, you'll probably have seen some of these ideas. And then we're going to move into chapter 2, starting with sections 2.1 and 2.2 on solving equations. Okay, so a few things to recall. So we have variables and expressions. These are important terms that we'll use. An expression is something like this here, this 7x minus 4. An expression is a little bit like a phrase in grammar, right? A phrase isn't a whole sentence. Maybe I say something like, the ball is on the floor. A phrase might be like the ball or the floor. We obviously usually have more complicated phrases than that, but in a simple sentence, the ball is on the floor. Those might be phrases, the ball or on the floor or something like that. So a phrase just expresses kind of an idea. So an expression in mathematics, this is like a phrase. Jeez. I don't know why my handwriting is so terrible there. This is like a phrase, or it's an idea. So this 7x minus 4 is what we would call an expression. This, of course, makes use of a variable. We typically represent variables as letters, as alphabetical letters. And these variables are just placeholders. They're just taking the place of a number to be filled in later. Maybe we don't know what number we want to fill in, or maybe later on we're looking for a number that we can fill in that satisfies a certain constraint. So these are often letters like A, B, C, etc., through, of course, the most famous one, X, Y, Z. X is the most common variable, but we could really, use any of these letters um, to represent a variable. We could even use, every once in a while, you'll see some Greek letters used, alpha and beta sometimes, uh, maybe say omega for something like angular frequency, or maybe gamma for something like wavelength. You might have seen some of these Greek letters come up in, physics or chemistry classes, things like that. Or what is gamma? I think lambda is wavelength. I forget what gamma is. But anyway, so you might even see Greek letters or different symbols used. But in this course, we're basically going to stick to our kind of standard alphabet, A through Z. And the most common letter will be X. But if we see a different letter, if we see a Y or something, that could be a variable as well. Okay, so what does it mean to evaluate the expression when X equals -3? Or remember, this expression, this phrase, has a variable in it. That variable is a placeholder. It's just a space that's being held open for a number to be filled in later. Well, this tells us what number we want to fill in, -3. So if I want to evaluate this expression, 7x minus 4, when x is -3, I say, okay, everywhere I see an x, just one place in this example, I replace that x with the number -3, and then I do some arithmetic to simplify this. I see I have 7 times -3 minus 4. Well, I have one multiplication and one subtraction. I remember my order of operations. Parentheses come first. I don't really have any parentheses here except for just the parentheses around the -3 to remind me that that's a negative number. But I don't have anything to simplify inside of those parentheses. No exponents. Multiplication division goes first. So 7 times -3 is -21 minus 4. And now I do my subtraction to get -25. So that's the value of this expression, 7x minus 4, when I substitute -3 in for the variable. If I substituted a different number in for the variable, I'd get a different number as the output. Now, what's an equation? So I mentioned an expression is like a phrase or an idea. If the ball is on the floor, the ball would be like a phrase. 7x minus 4 is an expression. What's an equation? Well, an equation is really actually a claim. It's a statement of truth. It's a claim or a statement of fact. So something like 7x minus 4 equals 3x plus, and let me think of, well, we'll just leave it at 3x. So this is a statement of fact. This is like a full sentence, right? The ball is on the floor. That's a statement of fact. That's a claim. If I just say the ball, that's just an expression. It really makes no claim. It's no statement of fact. Or if I just say on the floor, that's just a phrase. It's just an idea. It doesn't have any truth value. But if I say the ball is on the floor, well, I can look, and if the ball is on the couch, that claim is incorrect. Or if I observe the ball and it's sitting on the floor, I say, okay, that claim is correct. It's a claim, it's a statement of fact to say the ball is on the floor. Likewise, it's a claim, it's a statement of fact to say 7x minus 4 equals 3x. To say that the expression, the idea 7x minus 4 is the same as the expression or the idea 3x. There are two ways to look at equations that maybe are slightly subtly different. One is that I'm imposing this constraint, that I'm saying this is true, and let's observe the consequences of this. And another is to say, well, somebody told me this is true and I'm checking it. Right. So kind of, I think most of you have, solved an equation and then you go back and check your work. So you solve an equation and you get a claim, you get a statement of fact at the end, and then maybe you go back and you check to make sure that you didn't make an error somewhere along the way. Inequalities are just like equations. They're also claims or statements of fact or full sentences, but just in a slightly different form. Right? Something like 7x minus 4 is less than 3x plus 2. Right? So I'm saying that for the number that I put in for this variable, this left-hand side is a smaller number than this right-hand side. So equations or inequalities are kind of full sentences, so to speak. They're claims, they're statements of fact, where expressions are just kind of phrases or ideas. They're not full sentences. So what's the most important role of equations? The most important role of equations is that both sides of the equation must be balanced. So there's a couple analogies for this, but the one that I like is the envelope analogy. So if we imagine that we have a set of scales here, so if I put the same amount of weight on both sides, it'll balance and be level. If I put too much on one side, it'll, one of the plates will be lower than the other. And in my, I'm going to draw this, somewhat abstractly, but on my left scale over here, I have some, let's say, blue circles that weigh a certain amount. All the blue circles weigh the same. And on my right scale, I also have a couple of blue circles. Maybe I have some green boxes as well on my left scale, and maybe I have some green boxes on my right scale. And maybe at this point, these scales don't balance, but then maybe I have an envelope on both sides. And this envelope represents my variable. So I can see how many green blocks I have or how many blue circles I have. And this envelope that's on both sides, well, it contains some unknown quantity. And maybe I have one of these envelopes on the left side, and I have two of the envelopes on the right side, let's say. Now, each of these envelopes contains exactly the same stuff, but I don't know what's inside that envelope. I don't know how many green boxes or how many blue circles are in each envelope. In the imposition, if I'm going to say that these two sides are equal, if I'm going to impose that constraint, then often my goal is going to be to figure out that, okay, under that constraint, what has to be in the envelopes to make the scales balance out. Right? And keeping in mind that all three of these envelopes have to contain the same stuff. Now, let's say that I fill my envelopes up in such a way that both of these sides of the scale balance. What's the implication of that as I proceed forward? I've run out of colors, but what's the implication as I proceed forward and try to get down to where I just have, ultimately, I'm going to draw my scales a little messier over here. Ultimately, what I want is I want just one envelope by itself on one side and nothing else on that side. And then I want some stuff on the other side. If I manipulate this system in such a way that everything stays balanced, and I get down to just having my envelope on one side and having some stuff that has no envelopes on the other side, well, then I know that, maybe in this case, I'm just making this up. I don't know if this is the solution, but maybe in this case, each envelope had to have 3 blue circles and 2 green squares. Right? So my goal is to do manipulations while keeping the scales balanced the whole time to end up with just an envelope by itself on one side and some stuff with no envelopes on the other side. And then I know that each envelope must be hiding exactly this contents. To maintain balance, what I do to one side, I have to do to the other side. So, right, if I get rid of 2 green squares off of this side, I have to simultaneously get rid of 2 green squares off of that side. If I add a blue circle to this side, I have to simultaneously add a blue circle to that side. Otherwise, I'm going to be out of balance. I could even get rid of a whole envelope as long as I do it to both sides. I could toss one envelope from the right side as long as I toss one from the left side as well. And you can see what our procedure might look like here, right? I get rid of some envelopes until, well, now I only have envelopes left on my right side, and I only have one of them. And then maybe on my right side, I would get rid of some greens and get rid of some blues and do the same on the left side until I got just an envelope by itself on the right side and some green circles and blue squares on the left side. And then I know the contents of the envelope. So for our equation up here, 7x minus 4 equals 3x. Let me jump off to the side here. And let me change this around a little bit so that it works a little nicer with my model down here. Let's make it 7x plus 4. Yeah. And then 3x plus 12. I think that should work. Yeah. Is that? Yeah, that's gonna, okay. I don't want to turn out with fractions or negative numbers or something that'll kind of make my scales model a little more annoying to deal with. But I think of my two sides here, I won't draw the scales out anymore, but I will draw the red envelopes. So I have 7 red envelopes. And here we'll just use 4 units. 1, 2, 3, 4. And 3 envelopes on the right side. And then 12, 3 envelopes and 12 units on the right side. And again, I see I can maybe start with my envelopes. I can get rid of 3 envelopes on both sides. I'm imposing that everything started off balanced. If I remove 3 envelopes from the right side and 3 from the left side, everything should still be balanced. If I remove 4 blue circles from the left side and 4 blue circles from the right side, everything should still be balanced. So I should be left with 4 red envelopes on the left, and I should have 8 blue circles on the right. Or in other words, I should be down to something like 4x equals 8. And then we can just kind of visually pair these up. Each envelope gets paired with 2 circles. Or I could think of taking away 3/4 of the stuff on the left and taking away 3/4 of the stuff on the right. But we can just visually pair them off this way. I see each envelope gets 2 circles. So one envelope would balance with 2 circles, or we would say x equals 2. So as we move on to more complicated equations where we might have negative numbers coming up or fractions coming up, I think this is a good thing to just kind of think back to remember how this works. When we're saying, okay, I want to multiply both sides of an equation by a number, why do I have to be careful to distribute to all of the terms on each side of the equation? Well, because if I double the number of things on this side of the scale, I have to double the number of envelopes, but also double the number of blue circles, for instance. So I like this analogy. I think it's good to think back to, from time to time if things get a little more confusing or complicated, when things get a little more challenging. But this is the most important rule of equations. If you do something to one side, you can do almost anything you want to one side, so long as you do it to the other side of the equal sign. Okay, so one of the things that we're going to be interested in doing is checking whether a certain value, when substituted in for a variable, satisfies the claim, right? Somebody made the claim, the ball is on the floor, loosely speaking, take a look at the ball and see if that is true. Is the ball on the floor, or is it like on the chair or the couch or something? How do we do this? Well, what we do is we substitute in the value for the variable, we simplify both sides using arithmetic, and we see if we get the same number on both sides. Or in other words, if I said up here, I have my scales, the original setup before I started crossing everything out, I have 1 envelope on the left side, 2 envelopes on the right side. And if I claim to you that each envelope contains 2 greens and 1 blue, we'll actually put 2 greens and 1 blue over here. And in each of these, pull them out of the envelopes and see if your scales balance, right? So here, this is a claim. It might be true or it might be false when x equals 3/5. Let's check. So I want to check my 2 sides of my scales, my 2 expressions. Let me start with 5x minus 4. So I'll start with the left-hand side, simplify that first. You could write the whole equation out, but sometimes it can get a little bit tough to keep track of what statement you're actually making, right? We actually don't know if this equation is true for this value of x. So if I wrote like 5 times 3/5 minus 4 equals 10 times 3/5 minus 7, it's a little bit confusing what I'm saying there. Am I saying that I think this is true, or am I saying I don't know if it's true and I'm checking if it's true? So I'm going to take the 2 expressions independently and check them. So when x equals 3/5, my expression on the left, 5x minus 4, becomes 5 times 3/5 minus 4. 5 times 3 divided by 5, my 5's divide out, and I get 3 minus 4, or -1. As an aside, going through MAT090, there's going to be an expectation that you're, quite competent with the MAT080 material. And that does include fractions. So if you need a little bit of brushing up on fractions, use some of those useful websites in the Blackboard site, maybe Khan Academy or Math TV or something, go and drill some problems. You know, go to the review section in our book. But if you're running into some you know, challenges here and there with some of these fraction things or decimals or percents, whatever it may be, you know, just go back, review. That's part of the learning process, right? We never get into everything the first time around, so there are going to be some prerequisite material topics that when you see it in class, you say, oh man, I don't remember that as well as I thought I did. Well, take a half an hour this week, you know, go and drill some problems there, dust off the cobwebs. But our left-hand side simplifies down to -1. Now, if we evaluate our right-hand side and get -1, that's great. If we evaluate our right-hand side and get something else, well, then this wasn't a solution to the equation after all. So my right-hand side, 10x minus 7, when x is 3/5, becomes 10 times 3/5 minus 7. This is 10 over 5 times 3, or 2 times 3 is 6, minus 7 is -1. That's what my right-hand side becomes as well. Are these equal? Yes, they are. So determine whether x equals 3/5 is a solution to the equation. Yes, it is. So 3/5 is a solution to the equation. 5x minus 4 equals 10x minus 7. When I substitute the number 3/5 in for that placeholder x, everywhere I see an x, I end up with an equation. I end up with a scales that balance. I end up with an equation that with the same number on both sides. And I see that clearly once I simplify everything down to its simplest form. Right? It's really hard for me to tell whether these two numbers are the same. That's one of the reasons that math instructors harp so much on get things into simplest form. It makes it a lot easier to do things like tell whether two numbers are the same or tell which number is bigger than the other number. It's much easier to compare -1 to -1, or perhaps -1 to +5 and see they're different, than it is to compare these two complicated you know, messes of numbers. Okay, so the general format for this course is I'll introduce an idea. We'll go through maybe an example or two, and then we'll take a, you know, maybe typically 3 to 5 minutes or so, and I'll allow you to, on your own time, you know, work through a couple exercises. And typically what I'll do is, you know, let's say I'll give you 4 minutes to work through these two exercises. Maybe about, you know, a minute or so into that time, I'll jot down a couple notes on the first exercise, just in case you get stuck, kind of to, you know, get you over any barriers. Maybe you know, another minute or so in, I'll jot down some notes in the second exercise, and then I might go and, you know, write a little bit more, maybe not, depends on the problem type. And then we'll come back at the end of that and we'll quickly discuss the solution. Anybody can ask any questions. I'll typically also have chat open, which reminds me, my chat window went away. There we go. So I'll typically have chat open as well. So if you have any questions, you can pop them in the chat. But, you know, I do strongly recommend taking the time during these exercises. Don't take the time to, you know, check your social media or something. Take the time during these exercise periods to actually do the work. You know, don't use a calculator or something unless it's, you know, a problem that needs it, but try to do it by hand. Try to do it, you know, carefully as if you were taking a test. And, you know, if you get the question wrong, that's okay. Like, this is a low stakes environment. But if you get the question wrong, or if you get it right, that tells you whether you've understood the material that's been introduced. It's much, much, much easier in math to watch somebody do something and follow the steps than it is to create the steps yourself. There are some, you know, some fields and some courses where you can kind of just sit somewhat passively in a lecture and kind of absorb the material and really get most of it. Math, you really need to digest it and actually do it yourself to really tell if you've understood it or not. Okay, so on that note, let's take about 4 minutes, work through these two exercises, and this will be the rest of the course. You know, I'll do a question or two, I'll give you a couple exercises, and we just, go back and forth like that. So we'll take about 4 minutes to do these two exercises. And again, I'll jot a couple notes here and there. I'll actually leave this up on the page for the beginning. Here, work through these two exercises on your own. Take about 4 minutes. And after 4 minutes, we'll come back and discuss the solutions. Okay, it's just about 4 minutes, so let's touch base. Any questions on these exercises? So these are, fairly straightforward exercises. We're just moving into the material, so of course the questions that will get a little lengthier, a little more complex as we go on in the course. Um, but just a quick overview, of course, we are taking each of the expressions individually and evaluating them for x equals 1/3. That gives us the number 5 for the black expression on the left, 3x plus 4, and also the number 5 for the blue expression on the right, 18x minus 1. Both yield 5, and 5, of course, is equal to 5. So is x equals 1/3 a solution to the equation? Yes, it is a solution. On the other hand, in the second exercise, we plug in or substitute y equals 1.5. I use the word plug in. Some math instructors get really, annoyed when people say plug in instead of substitute, but I don't know. I use them interchangeably. I think linguistically speaking, everybody knows what we're talking about when we say it. So when y equals 1.5, we plug that in. In the left expression, 6 plus 4y, 4 times 1.5 gives us 6. 6 plus 6 is 12, is what we get on the left. On the right, 2 times 1.5 minus 1, well, 2 times 1.5 is 3, minus 1 is 2. Well, 2 and 12 are clearly not the same number. Right? Again, why do I want to put things in simplest form most of the time? Well, because it makes it really easy to compare them. I can really easily see that 12 is not the same as 2. So no, y equals 1.5 is not a solution to this equation, right? I'm making a claim. I'm imposing a condition that 6 plus 4y equals 2y minus 1. That claim is inconsistent with the statement that y has to be 1.5. Those two claims cannot both be true at the same time. Therefore, we say y equals 1.5 is not a solution to this equation. When I substitute in y equals 1.5, I get the number 12 on the left, the number 2 on the right, and that is not a valid equation. That's not balanced. So y equals 1.5, not a solution to the equation. Any questions on that? Okay, so what is our goal in solving the equation? Our goal is what we say isolate the variable, or in the envelope analogy, get one of the scales, one of the sides with just a single envelope by itself, and all of the other stuff on the other side with no envelopes on the other side. So we isolate the envelope to one of the scales by itself and no other envelopes on the other side. Or in more mathy terms, we say we isolate the variable. There's a little detail here. I bring this up mainly because you might have seen instructors that were really strongly in one of these camps or the other in the past. So there's an important detail related to what we call solution set notation. So often we'll see solutions to equations written as something like this, but you might actually say to yourself, well, I mean, if I say x equals 2, or if I write my answer in terms of this balance of scales here, I haven't actually like opened up the envelope and seen what's inside. I haven't said what's inside the envelope. I've just said these two scales balance now. Some people get very pedantic about this, and they say, okay, well, x equals 2 is still an equation. That doesn't count as a solution. It's an equation. And the solution should be phrased something like this. The set of solution to the equations is curly bracket 2 end curly bracket. I think this is, in this context, far too pedantic. So I don't use this solution set notation idea here. That being said, there are good reasons to use it, and one of the main reasons to use it here is that we do kind of need this notation later on, or at least we need to understand some aspects of the solution set idea later on. So particularly for things like graphing lines, things like that, this idea of solution set is more important there. But as far as I'm concerned, if you write x equals 2, like that's sufficient for saying that the solution is 2. Technically speaking, this is still an equation, but it's a trivially solvable equation. You just put the number that's on the right in for the variable on the left, and then you have a correct equation. So I think something like x equals 2, I would call a solution. You know, people will say, well, mathematically speaking, this or that, but really this is a question of linguistics. It's a question of how we communicate ideas, not a question of what the underlying idea is. So this is fine with me. I just mentioned this in case you've had instructors, you know, in your past math experience who really harp on the idea of always write out a complete sentence that says something about a solution set. I don't find that important at this point. However, um, if you're used to doing that and you want to do it that way, I don't think there's anything wrong with that. And you know, they do have valid arguments on their side as well. So I don't think their side is silly or completely incorrect. It's just that, you know, in my mind, the balance tends a little bit differently than in their minds. Okay, so now what are we looking to do? Well, now we're looking to move into solving equations. In other words, I would like to find a value or perhaps values that I can substitute in for the variable that will result in a correct equation that will result in a solution. I want to solve the equation. I want to find all solutions. I want to find all values, all real numbers that I can plug in for R and get a valid equation here, get a balanced equation. So that's what it means to solve an equation. Find all values, in this course, all real numbers that I can substitute in for the variable that will result in a balanced equation. So something like this, R plus 1/3 equals 1/2. Well, here I have kind of like on one side of my balance scales, I have an envelope and, you know, one whatever blue circle or something representing 1/3. And on my other side, I have, you know, some green square representing a single 1/2. So if I have that, let me actually draw that out. So I have my envelope and a blue circle where the blue circle represents 1/3 of a unit of mass. That's on the left side. Suppose my scales don't work very well if everything is full of helium and floating above them, but I think you get the idea. And my, you know, green square on the right-hand side. Now for my scales, what I want to do, I want to remove a blue circle from each side of the scales. So I want to remove a blue circle here, and I have something like a, you know, negative blue circle here on the right. At some point, any analogy starts to break down, right? But if I, you know, imagine having like a negative blue circle along with a positive blue circle on the right, like you know, whatever, an electron and a positron or something that like, you know, cancel each other out. I could remove my positive blue circle from the left, remove it from the right, leave me with a negative blue circle on the right. And I've got my envelope by itself. So practically speaking, what does this look like when we're just going through the algebra steps? Well, I can do the same algebraic operation to both sides of the equation. My goal is to get the R by itself. I need to get rid of this plus 1/3 that's kind of globbed onto the R, that's attached to the R. I want to get rid of that. I can get rid of a plus something by doing a minus that same thing, right? Because plus 1/3 minus 1/3 is 0. I can subtract 1/3 from the left side so long as I do it to the right side as well. On the left side, R plus 1/3 minus 1/3, R plus anything minus that same thing is just R, right? Because the plus 1/3 minus 1/3 nets out to 0. And on the right side, I have 1/2 minus 1/3. I've isolated the variable. I'm almost there. I probably want to simplify this number on the right-hand side, though. 1/2 minus 1/3 isn't a very nice simple number, but I see that 1/2 is uh, 1/2 is jumping the gun here. 1/2 is 3/6. There we go. And 1/3 is 2/6. And 3/6 minus 2/6 is 1/6. So I've done my algebra at this point, but then I still want to do some arithmetic simplification to get my answer in a pretty nice form that I can understand a little better, that I can maybe compare to other answers or whatever I might be interested in, or that I can, if I want to, check. I can check my work by plugging r equals 1/6 back in. I'm making the claim here that r equals 1/6 is indeed a solution to r plus 1/3 equals 1/2. I can check that by substituting back in. I might have made an arithmetic error somewhere, or maybe an algebraic error somewhere. I might have made a mistake. Let me check my work. Is it true that 1/6 plus 1/3, my expression on the left side, is it true that that's equal to 1/2? I mean, the right side expression is a little boring, but 1/6 plus 1/3, let's get a common denominator. 1/6 plus 2/6, multiplying that 1/3 on the top and bottom by 2. Well, that is 3/6, and 3/6, of course, is 1/2, which is exactly what I have on the right-hand side. No simplification needed on the right-hand side. So yes, it is indeed a solution. And I've actually done a little bit more than I might even realize. I found a solution, 1/6, but I've also kind of implicitly argued that 1/6 is the only solution, right? If I can, subtract in some sense a blue circle from both sides, if I can subtract that 1/3 from both sides, what value could R be other than 1/2 minus 1/3? I mean, I went through valid algebraic steps, isolated R, and this is what R has to be. I can't instead choose to add 1/4 to both sides and get R by itself, or I can't instead choose to multiply both sides by 2 and get R by itself. The only way to get a plus 1/3 off of the left side is to subtract 1/3. I can't add or subtract something different or multiply or divide by something different and get that 1/3 completely off the left side and isolate that R completely. So I've actually done a little more than I might even realize. I've shown that R equals 1/6 is the solution, and I've actually shown that it's the only solution. Right? Sometimes folks will ask, well, why can't I just guess the solution, right? If I can guess the answer, why isn't that a valid approach? And there are a couple answers to that. We don't want to just guess and check because, well, maybe for something like wherever it was up here that the answer was 2. So this one here where the answer was 2, there. Maybe I would have got lucky and guessed 2. Do you really think that you're going to get lucky and guess 1/6 is the answer? Probably not, right? Or if the answer is 3.71, you're probably not going to get lucky and guess that one. No matter how much, it's going to take you a really long time of guessing and checking to come up with an answer like this. But even more importantly, philosophically, what's the method of thinking in mathematics? Even more importantly is, well, if I guess a solution and check and maybe it ends up being right, is there another solution? Does this problem have maybe 2 solutions or 3 or maybe even infinitely many solutions? I don't know. I would have to guess and check all of the real numbers to know that. But by going through a set of carefully defined algebraic steps, I've also implicitly argued that this is the only solution, that there's exactly one solution to this equation. You might think to yourself, well, I mean, isn't there only one solution to every equation? And the answer is no. We'll see quadratic equations that often have 2 solutions. We'll even see linear equations that can have infinitely many solutions. Equations that look more or less kind of like this one or this one, they can have infinitely many solutions. So we do have to be a little more careful. There's good reason to follow this process to do these algebraic steps when solving our equations. Not just because some of them are going to be really hard to guess and check the answer, to happen upon the answer 1/6, but also because implicitly there's more going on in the background here. We're implicitly checking that we've gotten all the solutions. If we happen to find a solution by guessing and checking, we never know if there's another one floating out there somewhere that we just haven't quite gotten to yet. But if we do the algebraic steps, we will be able to implicitly argue that we found all of the solutions as well. Okay, looking at something like this next one, this one looks a little more complicated. Solve the equation 4m minus 1 minus 3m plus 7 equals 5. This left-hand side is a little more complicated than the previous expressions we've seen, but nevertheless, it is still just an expression. When I have something like this, I don't want to jump right away into moving stuff around between the sides of the equal sign. That can get pretty complicated pretty quickly. What I want to do is I want to simplify first, right? I always want my complexity curve, I want to look like this. I want to get less complex before I make something more complex, less complex again before it gets more complex. If I do something like this, kind of climb this big mountain and try to work my way down the other side, difficulty, this is true in math and also true in life in general, difficulty scales non-linearly with complexity. If something's twice as complicated, it's like 10 times as difficult. I want to manage the complexity. I want to always, after each step that I do, or even before I do the first step, I want to simplify everything to be as simple as possible. And then I want to do an algebraic step. And then I want to simplify again before I do maybe another algebraic step. I want to simplify after every step and really even before the first step. So I take a look at this left-hand expression here and I see I have some like terms. Let me choose to group those this way, 4m minus 3m, and then I'll do plus 7 minus 1. Using some of my commutative properties there, or using my commutative property a few different times, I guess is the better way to say that. And I see that my 4m minus 3m simplifies down to 1m, but we never really write the 1. If we have 1m, we just write m. My numbers here, plus 7 minus 1, simplifies down to a plus 6 equals 5. Now, again, this might be one where we can guess and check the answer, but by carefully going through the algebraic steps, we're going to also confirm that that's the only answer that we have. My goal is to get this m by itself. Everything's as simple on each side for each expression that I can make it. So now I'll do an algebraic step where I subtract 6 from both sides. The goal being to get that plus 6 off of the m. I do that by subtracting 6. M plus 6 minus 6 just gives me m plus 0, or just m on the left-hand side. 5 minus 6 on the right-hand side is -1. And then I would go back and I would check in my original equation. For time purposes, quite often I won't actually demonstrate going back and checking. But as you're going through your notes, it's not a bad idea to go back and actually check each of these problems that we do. Plug the -1 back in to the original equation before we did any work, simplify down, see that you get left and right side that are the same. Okay, for our last 12 minutes or so here, we will work on these two problems. So again, two pretty similar problems to the ones that we've just seen. So take maybe about, I think 4 minutes should actually probably be enough for these as well. So take about 4 minutes, and same thing. After a minute, I'll write a couple notes. After another minute, I'll write a couple notes, and then we'll come back in 4 minutes and discuss the answers. If anybody has any questions in the meantime, pop it in chat, or when we come back, if you have any questions or thoughts, we can chat, we can discuss then. But take about 4 minutes and work through these two problems. Okay, we're right at about 4 minutes now, so let's take a quick look back through these two problems. So we had r plus 7/5 equals 3/10. Um, as I noted here, nothing to simplify here. Both sides are pretty simple. Um, when we get to later sections, we might decide to clear fractions first, but I think here it's actually easier to not clear fractions first. Um, So just in case you're thinking, hey, I kind of remember this idea when there are fractions, we want to clear fractions. Why aren't we doing that here? Well, two answers. One, we haven't quite gotten there yet. And two, in this problem, it's actually easier to not clear fractions. So, um, but we say, okay, nothing to simplify. My goal is to isolate the variable, the r, get it by itself. Right now, it has a plus 7/5 attached to it in its expression. How do I get rid of a plus 7/5? Well, I subtract 7/5. I can do that to the left side so long as I do it to the right side as well. So I subtract 7/5 from both sides. On the left side, on my expression with r, the plus 7/5 minus 7/5 just nets out to a 0. R plus 0, of course, is just r. And on the right side, then I have 3/10 minus 7/5, and that just is what goes on the right side. Now I've isolated the variable. This r is by itself. Its expression is only just it's the variable, right? And all of the other stuff on the other side is only numbers. But now I can simplify again. Or well, not again, but I can simplify. 3/10 minus 7/5 ends up being negative 11/10. So r equals negative 11/10 is my answer. And again, ideally, I would go back, plug this into the original equation, uh, arithmetically simplify both sides, and check that I get the same answer on both sides. For time's sake, I typically don't do that in class. I might do it every once in a while. But I do recommend that you do that on each problem. I just don't want to spend too much class time going through that's more an arithmetic exercise than an algebra exercise. For this next exercise, let me leave this one up on screen. For the next exercise, again, we have this complicated left-hand expression, 4m plus 3 minus 3m plus 7 equals 5. The right-hand side, nothing I can really do to simplify that, but the left-hand side, I notice that I have some like terms, this 4m minus 3m. I can just kind of put those together near the front of the expression, and the plus 3 and the plus 7, put those together near the end of the expression. I like moving things first to get them together, and then combining them. I think it's just a little easier to make sure that you don't miss a term or make a mistake somewhere if you kind of move them and then combine them in two different steps. And that's often the case in math. If you do things in a couple different steps, again, each step is less complex, so significantly less difficult overall, right? Doing two easy steps is a lot less difficult than doing one hard step. The same way that lifting 10 jugs of water from the floor onto your counter one at a time, even for all 10 of them, is a lot easier than doing one lift of like all 10 of the jugs of water all at once, even though I think every guy likes to try to get all of the grocery bags in on one trip. That's not the easiest or most efficient way to do it. But anyway, so I move the terms around. 4m minus 3m is 1m, or we just write that as m, plus 10 equals 5. Now I've gotten both the expressions on both sides, as simple as I can get them. There are no like terms left to combine, no simplification left to do. Now I look to do an algebra step, an equation solving step. I see that I want my m by itself, but right now it has a plus 10 attached to it. How do I get rid of that plus 10? I subtract 10. So subtract 10 from both sides of the equation. That leaves me with just m on the left-hand side, and then 5 minus 10, or negative 5 on the right-hand side. So m equals negative 5 is the solution I came up with. And again, ideally, I would go back, plug that into the original equation before I've done anything, and then simplify and make sure that both sides net out to the same number. So essentially in this case, making sure that that left-hand side simplifies to 5, since we can clearly see the right-hand side is just going to stay at 5. Any questions on any of this? Okay, I think we will stop there. When we come back, we'll pick up on we'll pick up with this topic with some examples that require maybe a little more simplification up front. Talk about a couple of word problems, and then jump into 2.2, and we'll kind of hit the ground running next time. So have a bit of a long weekend this weekend. So we have Monday off for MLK Day, but we'll be back here on Tuesday. So next Tuesday, come in, be ready for jumping right into section 2.2 and continuing from there. Are there any questions on anything that we've talked about today, or questions about the course in general? All right, then I will